Our paper is titled Distributed Model Predictive Control for Cooperative Multi-Rotor Landing on Uncrewed Surface Vessel in Waves. My name is Jess Stephenson, and this work was done in collaboration with Nathan Duncan and Professor Melissa Grief with the Robora Lab Group in Ingenuity Labs at Queen's University. Working as a heterogeneous team, multi-rotor unmanned aerial vehicles, which I would refer to as the multi-rotor, and unmanned surface vessels, the USV, can enhance maritime robotic applications such as advanced search and rescue operations, Coast Guard surveillance, and remote monitoring in the Arctic. For these applications, the ability to land a multi-rotor on a USV for tasks such as recharging is critical. UAVs are agile and provide high-speed aerial information but have a shorter battery life, while USVs offer extended battery range and may be better suited for other marine tasks but are constrained to the surface of the water. Autonomous landing of a multi-rotor on a USV presents two main challenges. Firstly, it requires safe and reliable performance despite limited communication between vehicles and in cases of communication loss. Secondly, when the surface vessel encounters rough water conditions, the location and timing of the landing is critical to prevent damage to the multi-rotor due to the tilt of the USV at touchdown. Given these challenges, our work will solve the autonomous landing problem and consensus problem in challenging wave conditions while minimizing shared information. Model predictive control is a common strategy for multi-rotor landing tasks. One proven approach is a centralized MPC. However, this approach does have some limitations. Firstly, it is vulnerable to communication breaks and delays as it requires communication with a single centralized station. Additionally, it involves solving a larger optimization problem, which is generally slow and computationally expensive. Another approach is a decentralized MPC scheme, which requires no communication between vehicles. Although this has been shown to be effective in landing a multi-rotor on the USV, the work assumes that the USV is stationary in space and waits for the multi-rotor. Considering the limitations of these previous studies, our approach will adopt a distributed MPC architecture where the USV and multi-rotor cooperate to achieve a self-organized consensus. A distributed MPC scheme has been applied in other work to landing a multi-rotor on both an unmanned ground vehicle and on a USV. However, the landing was treated as a rendezvous problem where both vehicles were required to converge to a specific location and time. The rendezvous point was known a priori or could be updated online. Additionally, the vehicles shared their planned or optimized trajectories. In order to maintain lightweight communication and adaptability, in our approach, the consensus location will not be known a priori and vehicles will not share their planned trajectories.
So building off that, the key idea of our approach to this problem is to treat the landing as a consensus issue. In that, both vehicles will have different goal locations that will be iteratively shared amongst each other and used to update their states and goals until they reach a consensus landing. In this work, we developed a model predictive control framework for safe multi-rotor USV cooperative landings that will leverage the agent's position within a spatial temporal wave model. We show in simulation how our approach can simultaneously coordinate in real time both a safe landing location and execute the landing tasks for a multi-rotor to a USV within harsh wave conditions. Our approach for the MPC utilizes three terms, the first being a standards tracking term, JTrack, that compares the agent's true position to its artificial goal and relative control inputs. This MPC is augmented by two other terms we created for this project, a co-op term, which compares the artificial goals of both agents, and a tilt term representing the local environment of the agent's goal within the wave model. We'll also be using the subscript M to denote terms related to the multi-rotor and subscript S to relate to the USV.
JM track and JS track are standard quadratic tracking costs for the multi-rotor and the USV respectively. Specifically, the tracking cost sums over the prediction horizon, the position error between the vehicle position and its goal, and the control effort on the vehicle U. QM and RM are positive definite matrices that weight position error and control effort. The tracking cost JS for the USV below has the same structure. Next, we include a cooperation cost, JM co-op and JS co-op. Each time step, the multi-rotor receives the USV's current goal and optimizes its own goal location to cooperate with the USV through JM co-op. The cooperation cost considers the goal position error between agents plus a holding height HD that the multi-rotor must maintain above the USV before landing. This and other constraints on the altitude prevent the multi-rotor from dipping below the boat. The cooperation cost for the USV JS co-op is similar to JM co-op, as at each time step the USV receives the multi-rotor's current goal and optimizes its own goal location to cooperate. WM and WS are positive definite matrices that weight goal position error between agents. In the MPC, we are now optimizing both the trajectory as before, as well as the goal position.
The final term of our MPC utilizes a spatial temporal wave model that outputs a wave's tilt angle squared. In the USV's MPC, this term's purpose is to optimize the surface tilt angle at the USV's goal location within the wave model. The wave model itself is passed the agent's goal and as an X and Y vector and a query time, and the output of that wave model is averaged over the wave's time period. For this term, the weighting matrix is represented by lambda. With regards to the multi-rotor agent, the tilt term is used to time the descent of the multi-rotor. Before the term is activated, the multi-rotor will hover at a set height above the wave crest. Then activation is determined by the multi-rotor's internal goals as well as information received from the USV. The three criteria for activation listed there are that the USV is at its current goal, the multi-rotor is at its current goal, and that the multi-rotor goal and the USV goal have reasonably converged. Together, these three criteria also imply that the true position of the multi-rotor has nearly converged to the true position of the USV. In the multi-rotor's tilt term, we sum the wave's square tilt at the goal location over the MPC's horizon. This term includes a static weighting matrix similar to the USV's term, but also includes a dynamic weighting function, h of e gz, which is based on the multi-rotor's relative altitude. At normal hovering altitude, the tilt term is dominated by the lambda weight matrix. However, when the relative altitude reaches about 16 centimeters, this represents a commitment point for the multi-rotor, where the weighting of this h function rapidly decreases and causes the multi-rotor to commit to a landing at that location, regardless of future changes in the wave model.
Spatial cooperation of the proposed distributed MPC is shown under three strategies. Firstly, the purely cooperative strategy, where no tilt cost for J-tilt for either vehicle is considered. Secondly, the pure this calm water strategy that leverages the novel spatial tilt costs derived previously. And finally, the ride the wave strategy that replaces the spatial tilt cost with a short-term tilt cost that considers only the current tilt of the USV instead of taking the mean square across the wave period. The purely cooperative strategy reaches a consensus landing location relatively quickly as the vehicles track their own goals and consider each other's goals through the cooperation cost. However, we observe that the agents do not account for the USV tilt at the location, which results in an unsafe tilt angle in the severe waves when the multi-rotor descends to the USV. Our proposed calm water strategy initially shows a similar trajectory to that of the purely cooperative strategy as the vehicles prioritize cooperation. However, in this strategy, the USV goal shifts to the right-hand side to minimize average tilt angle. We can see how tilt cost is driving both agents towards calmer waters. Once tilt cost is minimized, the USV and multi-rotor cooperate and the multi-rotor can land in the calmer waters.
In the ride the wave strategy, the tilt cost is replaced with a short-term tilt cost where the summing window, NS, is less than the period of the wave. In this strategy, once the two agents converge to the same location, their goals will settle on the nearest wave crest or trough, and then follow that point as the wave moves. It'll stick within this point as regions at the extremities are unfavorable with rising and falling edges of the wave. As the agent's goal position follows the crest of the wave, the agent's MPC optimizes a path to reach the goal within its horizon. And as the goal is continually moving, the agents continually persist and steps behind their goal. And so this strategy requires more work to overcome this lag. This slide demonstrates the temporal cooperation of the agents using the calm water strategy. In the upper animation on the right, the weighing matrix of multirotors is set to 0. This causes the multirotor to immediately attempt landing despite being located at the rising edge of a wave. In the bottom animation, with tilt increased to 20,000, we can see the multirotor does neglect the first 3 passing crests once activation is initiated, and waits for the USV to move further into calm waters before landing. The figure on the left side of the screen shows the altitude of the agents over time, and shows the same weighting conditions as before, as well as a few others. These figures here describe the landing tilt for various tilt weights as discussed on the previous slide. The general trend that you can see is the longer the multirotor waits and the further the USV travels into the calm waters, the lesser the surface tilt at landing will be. For the spatial graph on the right, the trade-off of the landing angle reflects the nature of the wave model. So the region of greatest improvement we can see is around 20 meters. And that's just a reflection of the wave model we used along with how it is interpreted by our MPC. And that gives a smoothness of the wave crest in that region that is relative to the horizon of the MPC. For the temporal trade-off, intuitively, the most time-efficient safe landing once the landing procedure commences is obviously to land on the nearest crest or trough. This point is seen on the graph where lambda is approximately 10 to the 4. And waiting past that point for further crests or troughs for smoother waves does improve the landing angle, but the agents tend to slow down as there's less incentive to move to calmer waters, and improvements in tilt angle take more time.
We show robustness of the proposed distributed MPC to temporary communication loss by preventing both vehicles from exchanging their goals for 10 seconds. We observed that as the goals were aligned before the communication loss, they hold their position together. Each vehicle moves towards the last known goal for the other vehicle. When communication is reestablished, the goals rapidly adjust to resume cooperation and tilt minimization. In summary, we have developed a distributed MPC architecture that can perform a cooperative safe landing by leveraging both lightweight communication and a spatial temporal wave model. This architecture can easily augment existing tracking MPC techniques for multirotors and USVs. Simulation results show how our proposed approach coordinates and executes in real time a safe landing location and time for the multirotor to limit severe tilt of the USV. Additionally, the simulation results demonstrate the robustness of the system to temporary communication losses and delays. Thank you.